All right, now for our final part of our dynamic distillation column. Now we're going to be plotting the McCabe-Thiele diagrams. Of course, we want to plot, first of all, we have now a changing reflux ratio, which that's why we defined our ramping function. So now, along with our distillate that we're ramping up to be half the feed from the previous video, now we're also going to be ramping our reflux ratio in the same manner with the given conditions shown here. Once we do that, we'll also do the McCabe-Thiele diagrams pretty much with 5 separate intervals. Of course, the same 300 seconds used before. Now I'm actually curious with this part 1 if they actually also want to look at our time dependencies from the previous graph. So, I mean, we could also look at that as well. But yeah. Yeah, let's just go into it. I think I'm overthinking things. So head on to our collab here. This is from our previous video, had this all coded up. Though I think there were a couple of mistakes that I caught kind of rewatching. One of them was this omega, or not omega, but we called it W for our weird constant, experimentally determined. And actually, this is actually the good time to go back to our drawing board here. I think I made a note right here. So this W should actually be inside. I have no clue why I drew it outside here, since it's actually one of the first things we move over to the other side when we're isolating our initial value for the condenser, that initial value for the moles of the condenser. So yeah, that omega, or not, I keep calling it omega, that W should be inside this 2/3 power. So go ahead, switch back and go to change that. So right here, had the W outside. And of course, it made no difference since the W was 1. But of course, if that W changes, now that's where we have a problem. So move that parentheses over and we should be good. Let's run that. I was practicing earlier. There were some things with the NP where. So it looks like I did code it in this instance. This is definitely an important part. Let's zoom in here so you can see better. But this NP where, this condition where the moles, if it's less than the holdup, obviously the flow should be 0. Again, we discussed this in a previous video, but this is definitely an important condition we should keep, since obviously if we don't have this condition, we'd be running this expression even if our moles were less than that. So we have a negative in there. And obviously that means less moles for some stages, more moles for others. So just a different condition overall if we didn't include that. So good thing I included it there. Here. I think we had everything. So I guess we can simulate this with a we can just copy paste this honestly once we have our ramping function. So actually let's go ahead and do that. If I can just do this, I'll split this to there. So yeah, we want a reflux ratio of from 2 to 5 over 10 to 100 seconds. So go back up to our right hand side function, and now we're going to be including this reflux ratio as a function of time. So obviously this needs to be a parameter. So we can call it something like reflux ratio function. Of course, now we need to get rid of our r is equal to 2. Now it's not a constant, it's a ramping function. So I'll just put it up here where we define it now as r is equal to our reflux ratio as a function of time. So that's that. Shift enter. And what we want to do is in our solve IVP, this instance of defining, you'll notice that we didn't actually provide an initial value for the right hand side, or not right hand side, reflux ratio function. And the reason for that is we're actually going to include it in our solve IVP parameters. So, you know what, let's just do full screen here. This instance of having a function that's not called in your parameter happens so often such that it's actually a parameter within solve IVP, and we call this the arguments. So if it's not provided, we have the arguments, and then within the arguments, we have our, what do we have? Well, in this case, we're just going to keep it constant, but in the next case, so this is result 1. For result 2, when we run this again with the end steady state of, well, result 1's steady state as the initial value for result 2, we're going to want to actually include the ramping function, but in this case, we're just going to keep it the same. Honestly, we could just do something like, so we're going to use lambda. I guess this is our introduction to lambda, but basically, it's an anonymous function where it takes any number of parameters. In our case, our lambda is representing our ramping function, at least a function for it, so that we can use that expression of our ramping function. So I'll do something like, I don't know, lambda t. So this is provided the arguments for our parameter that we didn't provide, our reflux ratio function. And then we can just go something like 2, since that's what it was at the start before. So let's just check this to make sure. We should have the same exact values right here. So go ahead, copy paste that and see if it's still the same, which it should be. So I'll hit run all. Of course, it'll stop here. Here we go. I think it should be tuple. Is that right? Oh, I think I'm missing a comma here. There we go. So this comma here is to, I guess, provide for any other arguments that we have later on. And you'll also notice that this is a tuple, so we'll need to, when we do this again for the ramping function of the reflux ratio, we'll actually need to do a list. And then again, we did this before with the, when we are graphing right here, we did kind of a little list in a loop within a list, nothing crazy, but we're going to do the same thing. So just a heads up. Let's double check this. It should be the exact same. So this is our y, 2.7, and then down to 8.94. Okay, it looks like we got the same, so no need to worry. All that's good. Hit run all. Why not? Yeah, this is our first result that we did in the previous video. All I did is now we're adding our reflux ratio function. Yeah, I think that's all we have to do there. From now on, it's just, now we're going to unpack our, well, actually, yeah, let's go into the side about the lambda. So just more about the lambda. So you'll notice we can kind of set it to a variable, and this is an anonymous function. So it's different from how we normally call a function. So I guess we can go something like define x. Oh boy, come on. So define x, and we give it a number of parameters, maybe like a, b, c. And then we just tell it to return our expression. And okay, maybe just add those up. Let's say that. Obviously, with more functions, more complex functions, they're going to have more lines of code. But for something like this is a good example of, I don't know, we can go a equals 1, b equals 1, 2, maybe c equals 3. Then if we do x, a, b, c, we should get all those. Oh, just space them out. Go. So obviously 1 plus 2 plus 3, 5 plus 1, 6. So again, we could just do a lambda here. It's kind of a substitute for that function. So lambda takes a number of, any number of parameters, so we'll do the exact same. And then we tell it to, with our expression, where it's just adding them all up. So if we do the exact same thing here, provide the same parameters, you get the exact same thing. So nothing crazy, but you can see it kind of gets more useful with kind of more complex functions. When I say that, we're actually, to kind of showcase the power of a lambda function, we're going to be doing something called like, I don't know how you want to say, like embedding embedding the lambda within a function. So what I mean by that is we'll go ahead and define a function, call it like some power. So it's a function that will take a power and we want to return the lambda. So this lambda is the expression of the actual calculation of the of this function, and that's just taking in. It'll take a number. So this actually isn't provided in the current function. Some number, a base number, and then we'll take it to the power, and that's some power of n. So hit Shift Enter on that, and then we'll go ahead and define, like our power. So like you have square, cubed, I guess quad for to the fourth. So I'll go ahead and do that. So we have square, squared is equal to some power. So now this is a variable equal to a function, but this function is initialized. Well, we're giving it a parameter. So for squared, obviously that'd be 2. And you'll kind of do the same thing for all the other ones. So obviously one will be cubed to the third, and then quad to the fourth. And I heard quad is actually called super cubed or something along those lines. But anyways, so yeah, we have variables that are set to our function at a set parameter. So now if we actually, these are actually functions themselves. So if you supply a number, I don't know, let's do, I guess it's kind of obvious if I call it A. So maybe I call it B, and you'll see that the B is actually A, and I don't know, maybe it's easier to see if you actually see the numbers. So maybe we'll do B equals 2, and then we'll do squared of 2, or squared of B, I'm sorry. We'll do the cubed of B, and then we'll do the quad of B. So this B is actually A. I don't know why I'm calling it B, but it's just kind of to showcase where this A is coming from. If I called it A, maybe you would think this A is in here, but in fact, it could be anything. Again, whatever we put in our function, it just takes in what it is. It doesn't really care what it's called on the outside. It cares about what it's taking in. So you'll see we kind of use a nested lambda function. Well, embedded our lambda function within a function. So now we have all these other functions calling our some power function, but you notice we only needed to write our lambda function once. So again, with increasing complexity, if you know you only have to use this expression once, and that's that, then you can call it off to lambda and use the lambda function. But at the point when you realize, oh, I need to use this expression more than once, well, we might as well just call it an actual variable name or a function name. So yeah, we called the sum power function, but we actually only needed to write the expression for the actual calculation once. So again, that's just showcasing what a lambda function is. Go ahead and delete that. That's my aside on that. More for me, honestly. So yeah, go ahead and run all. Why not? So what are we actually doing? We want to graph the McCabe-Thiele of our current results, and that will kind of just help us as an example for our result 2. We're pretty much going to be copy pasting the lines of code we wrote for that in our 5 plots for the McCabe-Thiele of our second result, where the second result is again with the ramping reflux function we have. I don't know if I want to start deriving, or not really deriving, but we can go ahead and I guess unpack our variables. I think we actually already unpacked it right here. So if I do something like, so this is, let's just look at it. Why not? This should be all of the moles, and I don't know why I did that. This is the moles and the mole fractions of evaluated at our t-plot. For all the times we said, again, t-plot was, what did we say it was? I think it was 0 to 100. If I can scroll up here. Yeah, 0 to t end, which t end was 300 up here. Well, I don't know why it's up there, but anyway. Yeah, this is all 300 seconds. So if we want to just get, again, from McCabe-Thiele, we're only interested in the steady state values. Again, the steady state values and the pairs of the x and y's correlate with our equilibrium curve, and that's exactly what we want to draw our staircase and our binary xy diagram for the McCabe-Thiele. So yeah, if I want to kind of collect those values, I would do something like, I don't know, maybe we can just capture those values right now, maybe. Let's do something, thinking class of these like X steps. So, because we already have our X's, or do I want to, I mean, I could do it also within here. I could call this, if I add, so again, our res1 solved t-plot, this is our array. If I want to get the last values, I could do something like from the start to the end and capturing only the last value, we would get our equilibrium. Maybe that's what we want to do. But I think that'd be confusing since we already had it up there. So I'm actually just gonna, maybe I'll call it like equilibrium or like steady state. Maybe like steady x's maybe. And then I'll call it the x's at, so for all the x's of the mole fraction, and then at the last value, at the last time basically is what we want to do. Let's go ahead and look at that and see if that's actually what we got. Should just be one array. Perfect. So you'll notice that this should be the last digits of this, but actually we can go ahead and look, try to find it. So do something like this. So we're looking for the last time of our x's, our mole fraction. Well, I think actually these are in stages, so we won't actually find them like that. So I guess we can correspond here. So we're looking at the last array. And these are evaluated at our times. So at the very last one, for at least for our last stage, which is represented by this this array, we have our last number here. And maybe you can go one step up, our stage above our boiler. This was at this mole fraction, 0.145, and we have 0.145. I think we get the point. We basically just captured at each stage. Again, each array represented by one stage, if I can scroll up. And we got all those mole fractions at the steady state. I don't know why I deleted that. Hide this. Yeah, we have our, I guess, our steady state x's. Go ahead and view that still. I guess now is a good time to, yeah, let's draw this out. So I'll go back here, iPad, and we'll go ahead and draw this out. So basically for the McCabe-Thiele, again, we're trying to get, so we have our mole fractions, we just need to get our corresponding vapor fractions. And to do that, again, we use our constant relative volatility equation expression, which we can go back in the code for. I'm sure I'll bring it up again. But the reason why we're going back is how we're going to order those points. So it's kind of confusing if I just say it out loud. And I know I was a little confused trying to work this out. So I think drawing it out might be better. If you remember from our distillation column in separations, the first time we did this in a previous video, I can scroll down maybe. We had our mole balance with our operating lines. So I'll just go ahead and draw a little short distillation column. This probably won't cover all of it, but we'll go something like our, in this case, we only care about our mole fractions, so I'll withhold on trying to draw everything else. So I guess I'll do like stages, again, that are starting from our condenser all the way down. I won't draw this all the way out, but I hope you get the point. So we have our liquid fractions coming from each stage. And then obviously we'll have our vapor fractions. So something like that. Maybe I'll also draw another one. So then I draw our vapor going up. So our vapor mole fractions, we have Y4, Y3, Y2, and Y1. And if you remember from our believe it's our rectifying operating line. Again, this is a rectifying stage since we're above the feed, or at least we're assuming we are. I didn't draw a feed. But if you remember, we had a starting point for our rectifying operating line at y1 xd, or which is also equal to x0. Again, these molar fractions are the same since they come from the same stage. And maybe pairing this out doesn't make sense yet, since maybe I want to draw this out first. So we'll do something like this. So go our 45-degree line, our equilibrium curve. So this is just our binary XY diagram, y1, x1. And then we have our operating lines. So rectifying operating line, trying to move my stuff so I can draw a decent line here. Something like that. Maybe you could do a bit better. That's a little too much. And then our other operating line, our stripping operating line. Something like that, maybe. And then, yeah, we can just, we had a point, obviously, on the 45-degree angle line, where our y equals our x. So if the y equals our x, then that lies on the 45-degree line. So something like this, maybe. And obviously, going down, we'd label this as our xd or x0. So I'll go ahead and just draw this staircase for now. And remember, we touch the equilibrium line and we go to our mass balance, which is our rectifying operating line. If you remember, working our way down with the mole fractions and our mass balance, if we have our y1 and our x0, well, that's just our mass balances here. And if we know our y1, well, if we know our y1, then we know the x1 coming down, since we know they're in equilibrium with each other. So that's what this point represents, the x1, y1, and you'll notice this is also x0, y0. Something like this. If I can x0, y1, right there. So these are points, and again, we're going down. And you'll notice that we have a sort of pairing within, oh, it looks like we crossed it, so we can go down even further. So again, once we pass the Q line or the Q point, we go to that represents our feed. So we go to the, that stripping operating line, our mass balance for the stripping stages, and we keep going down. And I think you get the point here. So I think we actually stop there. So again, just labeling out these points since it's not too much. We're still at the same x1, but now we're at a different y, so this will be a y2. And you can see that makes sense since we go to our mass balance. Well, if we know, again, since they're passing streams, this is just simply our mass balance, where if we know our x1, we know our y2, and that's what this point right there represents. So just keeping this up. We have x2, y2, same x for a different y, so x2, y3, and the same x or same y for a different x, so we have y3 at x3. So if I write these all out in points, you'll notice the pattern. We have x0 at y1, x1 at y1, x1 at y2, x2 at y2, and x2 at y3, and x3 at y3. So you'll notice that the y's here are just repeated upon themselves, but remember that our mole fractions, we have, I guess, what's the best way to explain this? We have our mass balances where we touch the line. So this is actually a mass balance here on our operating line. And then when we have the same subscript there, we're at the same stage, meaning that these mole fractions are in equilibrium with each other. So that's when we touch our equilibrium line. So again, this is our mass balance right here. These were, I guess, maybe seeing it again with our passing streams makes more sense. But going up above, we have our equilibrium line when the x1, again, same subscript, so same stage, so x1, y1. This has to be at our equilibrium line, and you'll also notice that x1 and y1 are coming from the same stage. So that's all that's doing. And again, it just keeps iterating down, but we're curious about the pattern here, so we know how to order our points when we graph it on the McCabe-Thiele. So remember that the same subscripts correspond to the same equilibrium stage. So it's something like the x1 corresponds to the y2, or the x1 corresponds to the y1. So whatever mole fraction of the liquid has to come from its corresponding vapor fraction has to come from the same stage. So when you notice we're calculating these y's, we use our expression. I think it's somewhere written here, down here. We use this expression. Again, we have a given x, so we have to calculate our y. And again, notice same subscripts. So when we use this expression and use our listed x's, our steady state from result 1, where we just had a constant reflux ratio, and we had our distillate that was ramping up to half the feed flow. We haven't included x0 here, but when we do the equilibrium of that, we would actually have a y0. And we notice that's not included in our list here. So we actually, when we do our equilibrium, our expression relating constant relative volatility to y and x, we need to make sure that we don't include that initial value. And then obviously we'll need to duplicate in between our x's and our liquid mole fractions in between. But again, notice here, so that would be our index, I guess we'll say 1 to -1. So again, remember, if indexing, we start from 0. So this would be 0, this would be 1, 2, and so on. And obviously the last one is -1. That's just a shortcut way of writing it with our indices slices here. But remember that the last index is not counted, so we'd actually only double up to, in this case, the 4th index here. So again, with our last value here for our mole fractions, remember these are going to be from steady state from result 1. Again, with the bottom value, it is not repeated, because if we tried to repeat the bottom value, we'd be going down. There's not really a point of doing that. So we also have to remember not to duplicate this last value. And then with the y, I believe I already mentioned this. So with the y, we'll have to get rid of the y0 that's coming from the x0. So the mole fraction of the vapor corresponding to the distillate. Remember, at the condenser, there's no vapor coming out. We're just extracting our liquid, returning our liquid reflux, and then we're taking out our liquid distillate. So we'll have to take that y0 corresponding to the distillate, or the liquid mole fraction of stage 0, out of this y index. And then from that point on, it's just duplicating or repeating these values. And we don't really have to worry about this last value since we have the y3s here. So honestly, we'll just repeat those values. So yeah, all that being said, hopefully that makes sense. I'll try to explain as I go on too. So let's go back to our collab. I'll take a sip here. So now we have our steady state x's that I mentioned before. Let's go ahead and split this up. Oh. Something like this. That maybe. I don't know if we'll need this all the way through, but so we have our steady state x's. So this list of x's, our mole fractions, correspond to our x side here. But that side of our liquid mole fractions, these are just at steady state. So remember, we want to repeat, I guess, the values inside the parentheses, or that I'm highlighting, since those are the values in between, and then we don't repeat the top and the bottom. So to do that, I'm going to do, let's call this, I don't know what we called it in class, maybe like X points, something, X steps. I think we actually called it X steps. So I'll do this in a different one so we can see that there's duplicated there. So run that, and so this will be a row concatenation. We're going to combine values, so we have one index for our oh my goodness, our liquid mole fractions depicted on the left hand side there. So I want to row concatenate, remember use brackets. So we do our steady x's at so we include the first value, and then we want to repeat, so we use MP, I think it's MP repeat of our in between value. So we do, again, going back to our index of our liquid mole fractions at steady state, and we want to get from 1 to -1, as I wrote on the right. So that's in between. So the first index excludes, obviously we start indexing at 0 in Python, so we get the second element using 1, and then excluding the very last element, so that we use -1. And then the last parameter here, I think it says it up there, we use do to duplicate those values. That's the number of times we want to duplicate them. And then we add in our last value, our last liquid mole fraction in steady state. So that will just be at -1. So let's see if this works. Can't even see this. Let's just switch to full collab. Add an extra bracket there. And let's go ahead and display our steps. So yeah, this is, so we have our first value, fine, we didn't duplicate it. Last value, fine, we didn't duplicate it. And then notice our in-between values, 1 to -1, are duplicated, which is exactly what we want. Okay. Moving on, remember we said we were going to use our expression for constant volatility relating the liquid mole fractions and vapor mole fractions at equilibrium. So we did this. This is how we modeled our equilibrium with constant relative volatility. So all we need to do is we're going to take our x steps, what we're going to be plotting in our McCabe-Thiele, into plugging it into our expression right there for our equilibrium vapor composition. So I'll do something like our y's are equal to that. So I'll go ahead and just copy paste that, honestly. And then I'll do something like copy this, use our Control-Shift-L to highlight our using multi-cursor, and I just copy paste x steps, and I want to see those numbers. So you'll notice that these are not quite what we want. Again, going back to our drawing here, remember that when I said we were taking the using the equilibrium expression, we'd have an extra value of y here that corresponds to our liquid mole fraction at stage 0, our condenser. And you'll notice that that's the only value that's not repeated, so it must correspond to our first element from this array. So again, we have to take this out because there's no vapor coming out of the condenser. That's what we put in our y steps. And then I believe at the bottom, I think we could just duplicate, or these are actually all duplicated. So all we need to do is double this last value because, again, it corresponds to y3. Since after we get rid of this value, all these values will shift to the left. So this y1 right here will correspond to the x0 here. And it kind of offsets that array. So then there'll be a gap here, but we know that it's just, whoa, that was cool. We know that's just y3 duplicated. So this last value duplicated. So we'll go ahead and do that right here. Yeah. So how do we want to do this? I guess I can do it separately so you can see that it'll get rid of it, but eventually I'll just put these all together so it's not too messy. We have our y steps. And again, a row concatenation. simply getting rid of this first value. So all I want to do is call pretty much all these values back. So that's our y's from 1 to the very end, and I can omit that last value since we're including it this time. And then we want to add on this last value again. So I just call it at y is -1. So that array at -1. And let's go ahead and take a look at that and see if that's what we want. So we shifted everything to the left because we got rid of our first element. That's correct. And then we duplicated our last value. Perfect. So that's exactly what we want. Hopefully that makes sense. I'm going to go ahead and yeah, I'll go ahead and just combine all these. If I can highlight them. Because with this, we're pretty much done with our McCabe-Thiele. Oh, not. Oh, I don't know where this came from. All right, merge these. And so we can get rid of these display values since we already looked at them before. I don't know if I want to plot all of these now. Honestly, yeah, we could. I'm a little hesitant to put it all in one line of code. So let's go ahead and just make our next figure. What are we at? Figure 3. So figure 3, make subplots. And we want to add scatter to, so remember in our binary XY diagram, we had our 45-degree line. I'll make it this one. Then we also had our equilibrium line. And I guess I should also define, we can do it up here, why not? So we need to define, for our equilibrium line, we do something called, we call it like xplot equilibrium. So we're generating points for our equilibrium line. So we know that's from 0 to 1. And we can do like 100 points. And while you can put the y here directly, I like to have it separate so you can kind of see what's going on. And then this line doesn't get too heavy there. And of course, we're going to change those values. But so we have our xplot at equilibrium, and then we use the exact same formula, our expression, I should say, relating our constant relative volatility. And now we just need to make sure all of these are at the correct x value. So copy paste that. And yeah, so I said this was the 45-degree line. Remember, that's just from 0 to 1. So to plot points, use a bracket as a tuple. And then we had 0.0 and then point from 0. So these are our x's from 0 to 1. And then our y's are the exact same thing. Zoom in on this. Oh, go ahead and make that. And then for our, we need equal sign. For our equilibrium line, we need to plot these points since this is how we got our equilibrium curve, since we're just plugging it into our constant relative volatility expression. I believe we just need to put xplot EQ here, our equilibrium for the x liquid mole fractions, and then our vapor mole fractions here. Remember, we got this with our expression that we derived in the last video. So I'll go ahead and remove these since we don't need them. Could have used multi-cursor there actually. And then I do want to change the color. Let's do, I think it's line color actually. The line color. Do gray for the 45-degree line, and then for the equilibrium line, I want to be a little fancy. I'll make it like light blue. So we'll do RGB. I think, I don't know if it's parentheses or what it is, but I think it's just something like that. Like this. Don't quite remember. Oh, here we go. I don't quite remember the syntax for RGB if I'm being completely honest. So I'll just make it blue for now. Why not? We can change it later. Oh yeah, that's bright. So let me add a template. Do we have it up here? We should copy paste that. Make sure we're figure 3. And yeah, that's our line. It's a little wide. There we go. Something like that. Maybe go a little wider. So we're not quite there yet. We just need to draw our staircase. So that was we're just plotting our values we got up here essentially. So it's just our x steps and our y steps since we already have them all lined up. So I guess I'll do it right under here. We have our actual what we call this staircase. It's really bothering me that I don't know the RGB. I think it's like this, right? Maybe. What do we had? X steps. So X steps, Y steps. Yeah, I actually don't know what it was. Is it like that? Wow, nice guess. Okay. Oh, we had a nice staircase. So actually we should make this mode equals lines. I think it's lines with the string, comma. Okay. And let's actually make it the color I want. I think that's my RGB. Well, actually, I think I'm getting way too hung up on this, but let me go ahead and change it so I don't have to do this again. So I think I like a white here. There we go. Looks okay. Yeah, so that's our McCabe-Thiele. Nothing crazy. That's what it is of our result 1. So now that we have a McCabe-Thiele, I'll go ahead and combine these. That yeah, we're basically just gonna copy paste this for our 5 McCabe-Thieles for our next iterants of our right hand side, where we use our initial values of our previous steady state moles and mole fractions. So I'm actually gonna add this. We did the fancy like labeling the stairs last time with our McCabe-Thiele. So actually, I'm just gonna head and copy paste that again. More cosmetic for me since I like seeing it. But you'll notice that we have to. We're going to be doing an iteration, so a for loop for when we do 5 different plots, and that will of course affect our lines of code written here, and also our like nice staircase we have where we labeled it with arrowheads there. So I'm gonna head just copy paste this, and I think I did that twice. All I do is change the figure here. I don't know, I call this labels staircase or something. And then we just change our x's to be the actual ones we want. Same with our y's, and this should be good. Remove the arrows. Oh, I forgot a comma. Nice. So that's all that is. Yeah, in the future, I think for our annotation here, we have to add a reference so it knows which of the 5 plots to add these annotations to. And yeah, I think that's it. I'm going to take a quick breather here since I'm talking a while, so I'll pause here for a second. All right, moving on. Actually, I'm going to go ahead and reread this thing we have for our problem statement since it might be misunderstanding. If it wants us to, so yeah, we do actually want to look at our previous result ramping up. I mean, it doesn't say graph it. You know what? I won't graph it. I think that's extra stuff. I mean, you basically just do what we did last video, and yeah, you're just changing the initial value. So actually, let's just go ahead and do our second result, our res2, which is essentially applying our, what we're doing is we're using our initial values again from steady state. So pretty much this, but we have our steady state, so we have to grab the last values of this array. And yeah, we use that for our solve IVP initial values right here. Then we change our lambda here to actually be ramping. And yeah, that's pretty much all it is. I mean, we can try doing it with result 2. I think I'm just getting ahead of myself. So let's go ahead and do what we want. So what I said before, getting those initial values. I mean, we already wrote this line of code. We're kind of rewriting it over and over again. But I think what I'm going to do is just call it a, instead of splitting it up, I'm going to rename. So we actually want, I guess we can look at it before I actually do something. I don't even think it's splitting it. So get rid of that. Essentially what I'm going to be calling it is like, I don't know, like initial steady state or like post steady, post steady values, initials, something like that, initial value, post steady initial. And then if we go ahead and take a look at what I did earlier, so this isn't actually what we want to get. This is all the values. Yeah, pretty much all the values. If I took a look at the shape, I wonder how big it is. Yeah, pretty big. We had, I think, 100 steps for time. I mean, yeah, 100 steps for time. So that's why that's 100, and then 16. So 8 stages, and then 1 for our moles and 1 for our mole fractions that are changing with time. So if we want to just get the values of the last time, all I'm gonna do is tell this array to tell it to grab everything in the first array, so all the stages, but only grab the last values, so that when we actually look at this, it should give me the last values. So this includes our moles at steady state at the last time, and our mole fractions at steady state at the last time. So I wonder if this actually should correspond to what we had earlier. So right there, 0.71, 0.55. It got rid of it. What do we call it? X, steady X's. So yeah, this corresponds to right there. Perfect. So yeah, I'm kind of doing the same thing over and over again, but hopefully makes it more clear. So yeah, I'm literally just going to be plugging that instead of concatenating it in our solve IVP. I can just plug it right here for the parameter of our initial value. So I'm actually going to copy paste this and just change it to result 2. Call this result 2. And then instead of that concatenation, I can feed it all as one array. Same method, we need the solution, and then now we change our lambda. So we have, I think, let's check the problem statement. Can't quite remember what it was. I think it's like 5 from 2. So 2 to 5 over 10 to 100 seconds, right above me there. So go ahead and do that. So we take in a time. We have our base is 2, so we add it, and then we're ramping up 3. So from 2 to 5. So essentially we're ramping up that addition of 3. So we multiply it by our ramping function. We take a time, and then we're saying we go from 10 to 100. So 10 is our initial ramping, and then we end at 100. Remember, that was our parameters defined in our ramping function. And we need to put this in a tuple. And we're going to be doing our little loop for something like for T in T-plot. Do I have T-plot defined? I don't. I think I have it somewhere. There we go. They'll do that over the course of our T-plot, essentially 0 to 300. I'm just putting it down here so I know what I'm talking about. So yeah, that should be good. Let's go back to full screen. Yeah, I'm going to cut this down so you can kind of see it better. That maybe. That go away? No. It's really hard to see. Anyway, that should work. And then I need to provide an extra argument here, I believe. I don't remember. Am Oh, okay. Well, let's just see if it works. There you go. Yeah. I don't know where this comment needs to actually go. If it's here. That's outside. Right here. Or maybe I do keep it parentheses and I was my goodness. Yeah, it's asking for this. Is it inside? I don't remember the syntax. My goodness. Okay. I'll go ahead and check the syntax, so it's not just this. Okay, I don't know why I was doing it like that. We don't need to loop this. I think I was getting ahead of myself for we loop this for our we're gonna need to do another loop like that where it's within a tuple or a list for our titles later on, subplot titles. So I was getting ahead of myself. But we do need a comma, I believe right there. So there we go. Hopefully these are right. I actually don't know, but looks like we're still decreasing, so that's good. Getting higher separation with our, honestly, let's just look. Hard to see. Let's unpack it actually. So I'll hide this. Print that, not that. My goodness. Okay. Yeah, we're gonna basically do the exact same thing here. I mean, we could use the same names. I just add a 2 in front, so it's not super confusing. Well, though we do use the same names here, it's a problem. I mean, I could do it here. It doesn't really matter. So I'll do the same exact thing, but now we're evaluating result 2 at our same t-plot. And I want to look at our x. Maybe that's too much. I think I forgot to look at the last values. Let's do something like -1. And all of them except the last. There we go. That did change quite a decent amount too. Yeah. We have, well, those are our M's. So we have 0.71. So yeah, increased separation at the condenser. So this is our condenser. It's going from stage 0 all the way to stage 7. And then yeah, less separation at the bottom, just what you'd expect. Yeah. Looks like the feed separation went down too, which is kind of goes with what we saw here in our first goodness. Our first iteration of our right hand side. So yeah, in our looking at my iPad here, it says just simulate it. So I think it's good enough if we actually just did it and we saw that it did change. I'm not gonna go ahead and graph it, but feel free to. All we're doing is basically just rewrite this same line of code and change it for result 2. So right there. I wonder if it would work if I just copy paste it, which we can kind of look at. I'm kind of curious now. Put it right above. And change this to result 2. See what happens. If this doesn't work, totally fine. Oh wow. This is a very interesting shape. So yeah, we had our reflux ramping up. So definitely could see that. And then we do reach a steady state. So wow, this is actually pretty interesting compared. Though it is kind of odd. We do see, is this our bottom stages here? So the pink. That's our mole fraction. So I think this is like right before the condenser. Very different. Suspect like something's also wrong with our code. It's a little odd to see higher separation at lower stages, so probably something wrong. But I'm not gonna get ahead into details of that, since that's the focus of that's not the focus of our problem. So we'll worry about that if we need to, since we want to care about our McCabe-Thiele. Hopefully, I do this within a reasonable amount of time. We're already hitting hour 1, so yeah. I mean, I think I might just call it the same, so I can just copy paste this code. Honestly, um, I don't think there's much we change this, other than obviously the figure, um, maybe the t plot, but that's already defined here as well. Though we will need to change it to 5. So I don't know. We can call this. We can call it within the cell itself is what we'll reference, so it should be fine. Something like plot new. So that's going to be our same exact range from 0 to our t end, our time end at 300 seconds, but this time we only want 5 plots. And then we're going to be looping this within our range of t plot. So what is actually t plot? Let me take a look at that before I start doing something. I don't know what I'm doing. Something I don't know. Oh, can't spell. Lens space. Go ahead and take a look at that. Yeah, that's just 5. So if I want to loop 5 times, is it size? It is size. Okay, so I would loop for something like for t in a range of t plot new size. So that should loop 5 times, if I'm not mistaken. Try it. Cool, 5 times. Starting at 0, of course. So yeah, perfect. That's what we want. Yeah, honestly, well, I'm a little hesitant to copy it all now. We can do a little bit at a time, honestly. So for t in a range of 5, essentially, I will want to unpack our moles and our mole fractions, but really we only need our mole fractions. And I'm just going to copy the code since I don't have to rewrite it. And then we want to evaluate it at our new t plot. So this will be at different times. It'll be splitting up that 300 seconds into 5, essentially 5 plots. So we want to get those out. Honestly, let's just go for it. Probably a bad idea, but I'm ready. So shift that over. Let's take this out of the loop and change all the figure 3s into, I think we're at figure 4 now. Am I? Yeah, figure 4. Okay. Don't need to. Well, I guess I do need to make the subplot. So I don't know why. Let's slow down a second. Let's take these out of the loop. Put the things in the loop that we do want. um, over. Yeah, so we're gonna be plotting these up. Um, I guess the right way to do this would be actually graphing it and then looping it. But that we already did that up here, so I'm not too interested in that. I mean, oh yeah. So 5 plots, we need to actually make our 5 different plots. So we'll do rows is equal to 1, columns is equal to 5. And I'll make a note to myself to remember these subplot titles. That's something I was confused with earlier. I can spell. Um, let's just graph it 5 times without even doing this. See, just make sure, you know. So we have, I think we just add it here. I want to add it here. Why not? Yeah. Rows equal to 1. Column is equal to t plus 1 since we're iterating along t. Let's just try it. And then we can save this for the very end. See if that works. Wow. Okay, we have something. It's all squished, so let's make this bigger. Nice. Okay, we're going somewhere. That's cool. Yeah. So we have, oh, it happened. I think I'm just like not confident enough. Okay. Yeah, let's go ahead and try adding our steps. So to do that, we need to evaluate our, essentially we're just putting all of this code down here. We can leave this up here. Essentially it's just these down. And I'll do, how about I bring up, oh boy, what's over into the loop. I'll bring up our staircase so it's actually right underneath all that code here. And then, so we're unpacking our moles and our mole fractions. We want to evaluate this at our new t-plots. So it's actually in terms of 5 sections. I mean, I could just call this t-plot, honestly, but I already called it t-plot new, so why not keep it different? And then make sure this is at res 2. Yeah, is that all we have to do? I only see that. And everything else is the same. Oh, we do want to, so this is where it does change. So remember, I called it steady here, but in this case, it's just the current time. So I can just call these XSS. The more X's are current X, current XS maybe. Yeah, sure, why not? Because it's not technically at the last spot anymore. Because remember that second I did, well, it was originally like this, right? Essentially, this is calling it at the last time, but we're already getting, we're already evaluating it at the current t plot. So actually, I think we want to get um, all of the x's, but at the time. So I think that's what I want to say. But we do still we should change this name since it's not steady state. It's at our current time now. So I don't know. What do we want to call this? Like current x maybe. Is there anything else we have to do with that? Since that takes x steps, this takes x steps. Everything else should be the same. So let's try it. Let's go for it. Awesome. We got it. Let's get rid of that. I think it's here. Show legend is false. Then we're almost there. We're pretty much done, honestly. But I like to add my cosmetic steps, so do it. Uh, yeah, let's do our staircase first. Leave the subplot titles last. So I believe we have to add a reference, so that's just right before our text. It's a parameter. I think so. Function. Oh, that's function specifier. What am I trying to do? Um, what is this again? Annotations. Flatly add and like that. Type in like the reference loads on me. Here we go. So these references, obviously we know Plotly. It's JavaScript. We index from 0 to 1, or I'm sorry, yeah, we index starting at 0. So we'll have to add a value of +1. I think I already did that actually. Yeah, the t plus ones. So wow, multi-cursor is nice. um, so basically that's all we're doing, but we have to put it in as a string like this. So it'll be something like xref equals x1, and then we'll have to iterate that. So it'll be x1, x2. And to do that, we use the f string literal. It lets me add a string, well, as it implies. So I'll put these in for now, and then I'll put them all together. How about that? Something like this. Then it is not letting me multi-cursor. Sucks. So we have x as staying the same. So that was we have here. Xref is just x, but then to denote which of these plots is going to, so 0, 1, 2, 3, 4, we have to add our brackets here, this curly brackets, and we have to make sure we're iterating for our t. So we do t plus 1. And I just do the exact same thing here, but of course it's just y. I think that should be it. Again, this y, there's a reason I put t up here, and then y or I is used for again, this is kind of review from when we did this last time, but hopefully you can see that. This is pairing up the 2 points, zipping them up together. So these were the points at our staircases, essentially starting, well, it looks like starting from the second element. So it's numbered index at 1, and then it goes all the way to the very end and goes every other step. So that's what this second colon is for. So those pairs were zipped up together, and we enumerate them starting at 1, so that for I, we have a starting case of I is equal to 1 at the very first pair. And all that's changing is now we're having this reference, so it knows where to go, basically. I mean, I could change it just to show. I won't bother. Okay. Yeah, let's just run this. Oh no. Where did we go? Commas? Yeah, commas. Can't forget commas. Let's go. It works. Okay. I spent quite a bit of time trying to figure this out, but now it looks pretty decent. All we're missing now is just our subplot titles. I mean, at this point, it's been a couple minutes since we finished the actual problem, but I don't know. We like to be fancy. So let's do our subplot titles right here. I left a spot. So subplot titles here is actually when we use our list I mentioned before. So again, we use there's a name for this, like function specifier, I think. I don't remember. Anyway, we use our f literal. I think that's what it's called, literal string. My goodness, f literal string. F string literal. Okay, that's what it is. So interpolation, we're just adding in our a variable with our string. That's all that's doing. Same exact thing here. So we want to put in our variable of time, and we'll say like its time is equal to that many seconds. And then we'll do a loop. So for t in t plot new. So let's see how that looks. Oh, did I miss something? Didn't close it. Awesome. Beautiful. Looks like it's a little too wide. Let's make this shorter. Or yeah. Well, I'm covering it a little. That kind of sucks. I'm sure there's a way to move them down one, but I'm not going to do that since I don't want to take up any more time. But I do want to fix this title here. So you'll notice that it's actually pretty evenly spaced out here. But I do want to take the time to go over something called I think it's like a f string specifier or a function specifier. You know what? Let's just look it up. specifier string format specifier. I think it's that. Yeah, F strings, maybe. Anyway, it's it's a way we can format strings, so we can format them with alignment. We can do how many decimal places you want, how many zeros in front, if you want a negative in front, so many different things. I think it's a format specifier. Is that it? There we go. This one? I don't know. Something like this. But yeah, I won't get into the nitty-gritty of it, but I want to show to myself that I know how. So if we pick like a really bad T end, so something that has a bunch of decimals, and we run this, it should give us horrible decimals. Oh. So the way we format that so that it looks better is we put, watch me mess this up, a colon, and then we can specify how many digits we have for the width, and then a dot for the decimal. So we specify the decimals after this, so maybe like 2 decimals, and then that's our function, or our F for our format. So yeah, 6 is the width, and then I guess it includes the decimal as well. And if you don't have 6, it stops there. Oh wow, that's really scrunched up. Yeah, you can notice all the decimals went away. So that's that. I'm just gonna return it to how it was, since it was actually pretty nice earlier. Yeah, I believe that's all we had. Yeah, you'll notice for at least there's this change in the middle. But we do reach our steady state pretty soon, about halfway in actually. So our staircase hasn't changed. We didn't reach any new conditions. So this is, I assume this is where our ramping was. So 75 seconds, I think, in between our ramping. And then 0 is obviously right before. So the change is within this this one plot we have. And then we reach steady state after our ramping of our reflux changed. You see that it was less scrunched up here than it is with on the right hand side, where the staircase is much wider. We're closer to the 45-degree line, meaning our operating lines have shifted closer to that or I guess how you want to say, less of a slope. So I guess it has less of a slope. I don't know how else to describe it. Yeah, let's go back to our problem statement, see if we got everything. Yeah, I mean, it's only 2 things, but I like to go over many other things. So yeah, we simulated it over from reflex ratio, ramping it up from 2 to 5, and we actually also graphed it and decided not to bother since it looked like some things were a bit wonky, but going over that, okay, good, we're recording. Yeah, we did it over the same interval. For now, a ramping reflex ratio, we use our ramping function, and then we graph our 5 McCabe-Thiele diagrams with that ramping function. So I'll go ahead, just leave it off here. Yeah. I believe this is the last part, so hopefully we learned something new with our dynamic distillation, where we had our liquid dynamics modeled with our Weir formula with that molar holdup deciding an increase or well, yeah, an increase in liquid flow rates going down. All right. Thanks for watching.